Truewave fiber, today's fiber that takes you to the future. Winner, Circle of Excellence Award. Winner, Technology Award for Fiber and Cable. Winner, Commercial Technology Achievement Award for Fiber Optics. Winner, R&D 100 Award. In today's competitive business environment, the thirst for information is growing exponentially. Voice, video, data, multimedia, internet service, the list is endless. And the high-capacity light wave systems that support these exploding data demands are becoming more complex every day. Erbium-doped fiber amplifiers, or EDFAs, have revolutionized the design and economics of high-capacity systems. Operating in the 1550 nanometer region of the spectrum, where fiber loss is the lowest, erbium amplifiers reduce the need for electrical regenerators. Signals now remain optical for longer distances, improving system economics by increasing the distances between costly active components. Erbium amplifiers have several other key distinctions in conjunction with emerging technologies. In a dense wavelength division multiplex system, a single erbium amplifier can simultaneously amplify multiple wavelengths. 8, 16, 32, and even more wavelengths can now be combined on a single fiber for explosive capacity, while the information carried by each wavelength will be continually upgraded to the highest available transmission speeds. 10 gigabit per second time division multiplex systems are now currently available, and systems that double and quadruple these rates are being demonstrated in laboratories throughout the world. In 1996, Bell Laboratories crossed a history-making threshold with an experiment demonstrating a data capacity exceeding a terabit per second on a single fiber. In 1997, Bell Labs reached yet another industry milestone with a 32 wavelength system, each wavelength operating at 10 gigabits per second over more than 640 kilometers. And these components are close to being commercially available. In building or enhancing a new network, service providers face a critical issue. What type of fiber should be installed today? With installed cable representing more than one-half the total cost of a network, lasting at least 25 years, what fiber will most effectively meet the needs of emerging DWDM and 10 gigabit per second systems, while at the same time keeping pace with research experiments that are soon to be commercialized? Let's take a look at fiber deployment decisions over time. Transport networks are designed to operate in the regions where attenuation is reasonably low and dispersion, or pulse spreading, is minimized. In the early 1980s, conventional single-mode fiber was designed to operate in the 1310 window, where loss was reasonably low and active components such as lasers were readily available. Recently, systems have become available that take advantage of the lowest loss region in the 1550 nanometer window. Conventional fiber is not well suited for this new operating environment at 1550, as there is a high level of dispersion which requires the use of expensive dispersion compensation techniques to maintain spacings between regenerators. As these 1550 systems were being introduced, the conventional wisdom was that the best fiber would be one with zero dispersion at 1550, called dispersion shifted fiber, or DSF. Several long-haul network operators installed DSF. However, with the higher power levels available with erbium amplifiers and the multiplexing of many wavelengths on a single fiber, a new problem emerged in network design: nonlinear effects. One potentially harmful nonlinear effect is four-wave mixing. With zero dispersion at 1550 nanometers, wavelengths in dispersion-shifted fiber travel at the same velocity. As different wavelengths travel side by side for long distances down the fiber, a form of optical beating takes place that produces new wavelengths. These four-wave mixing problems increase exponentially with the number of wavelengths being transmitted. Four-wave mixing products seriously impair transmission by reducing the power of the original wavelengths while creating crosstalk and noise as the electric fields of the new and original wavelengths overlap and interact. In 1993, Lucent Technologies spearheaded a new generation of optical fiber with Truewave fiber, generically called non-zero dispersion fiber. By introducing a small but non-zero amount of dispersion in the erbium amplifier band, wavelengths are able to travel at different velocities in the fiber. Four-wave mixing is no longer an issue as wavelengths can now pass each other. With Truewave fiber, as additional wavelengths are added, no mixing products are produced. Even if the laser power level is significantly increased, the fiber remains free of these troublesome artifacts. Lucent Technologies offers two different types of Truewave fiber, one with positive dispersion and one with negative dispersion. Positive dispersion simply means that shorter wavelength, or bluish light, travels slightly faster than longer wavelength, reddish light. Negative dispersion means the reddish light is faster. Both types of dispersion have advantages in certain applications. Both types are equally effective at suppressing four-wave mixing, usually the most significant impairment, but there are other nonlinear effects which depend on both the sign and magnitude of the dispersion. For most terrestrial networks, where system lengths are typically less than 1,000 kilometers, positive dispersion fiber gives better system performance. A nonlinear effect called self-phase modulation leads to pulse narrowing, or a self-compensation effect in positive dispersion fiber. This effect enables the fiber to carry more power and therefore provides an increased margin for degradation. However, for longer spans such as transcontinental undersea systems, which can be several thousand kilometers long, negative dispersion fiber is preferred. As we'll discuss shortly, it's also possible to combine positive and negative dispersion fiber in the same system to take advantage of both. Now, let's take a look at upgrade options for conventional fiber. Just as it is possible to upgrade old train tracks with high-speed trains, so too can a service provider transmit at higher bit rates over conventional fiber. However, conventional fiber requires compensation for its high level of dispersion at 1550 nanometers. A variety of dispersion compensation methods are available. The most mature method is to use dispersion compensating fiber to reduce the dispersion. One of the disadvantages of dispersion compensating fiber is its high optical loss of about 0.5 dB per kilometer. For example, to compensate for the dispersion of a 120 kilometer length of unshifted fiber requires approximately 20 kilometers of dispersion compensating fiber. This introduces an additional loss of 10 dB into the path. The loss must be overcome by reducing optical amplifier spacing or by using more expensive optical amplifiers. Therefore, dispersion unshifted fiber requires the added cost of dispersion compensating fiber, more amplification, and additional costs for outside plant sites. Truewave fiber can go 6 times the distances of conventional fiber before requiring compensation. Even then, the amount of dispersion compensation is 1/6 as much, so your costs are lower. Lucent has recently announced an innovative new product called Truewave Balanced Cable, which combines the advantages of positive and negative dispersion fiber and allows systems to have the greatest possible upgrade potential. Half of the fibers in each cable are positive dispersion and half are negative. This balanced cable design allows systems to use an optimum dispersion management strategy, where positive dispersion fiber paths are spliced to negative dispersion paths. For example, at each optical amplifier site, or at a special cross splice in the middle of each EDFA span. The balanced approach produces a net dispersion for the entire transmission span of nearly 0. This allows 10 gigabit per second and higher bit rates over long distances with no added dispersion compensation costs, while still eliminating the problems of nonlinear effects because the local dispersion is always non-zero. In fact, by alternating positive and negative dispersion fiber, the nonlinear effects are smaller than with either type of fiber alone. Furthermore, the dispersion values in Lucent's Truewave balanced cable are chosen to allow systems to operate over the entire 1530 to 1565 nanometer erbium-doped fiber amplifier range. Truewave fiber is available in a wide range of configurations and cabling options. AccuRibbon cable contains several fiber ribbons. Ribbons improve splicing productivity by allowing technicians to splice up to 12 fibers at once. LightPack cable is a central tube cable that contains bundles of individual fibers wrapped with color-coded yarns. Loose tube cable features fibers in loose buffer tubes. All three of these cables can be used in aerial, direct buried, or underground applications. Power Guide is an all-dielectric self-supporting cable intended for use along aerial electric power right-of-ways. Optical power ground wire is also available through our partnerships with other cable manufacturers. All of these cable types are available with either 100% Truewave fiber or a combination of Truewave and conventional unshifted fiber. Truewave optical fiber and Truewave balanced cable products are innovations from Bell Labs that offer you a valuable competitive advantage in future-proofing your network. As bandwidth and network capacity demands continue to explode, Truewave fiber protects your investment as it minimizes expenditures when more wavelengths or higher bitrate transmitters are added. Fewer EDFAs, regenerators, and less dispersion compensation means lower costs and increased profits. We are Lucent Technologies, the inventors of non-zero dispersion fiber, technology leaders in multiple wavelength systems, and the visionaries of the totally optical networks of the future. We have commercialized our technology lead into manufacturing leadership as well, with the largest worldwide deployment of non-zero dispersion fiber, lightwave products, and wavelength division multiplex systems. The choice is yours. You can simply react to exploding network demands and risk falling behind, or take a proactive approach and prepare for change now with innovative and reliable system solutions from Lucent Technologies, the world leader in fiber optic systems.